Okay. So, last time we started deriving the modulation response of a laser diode with the idea that we wanted it to be larger than that of the LED. It was a little bit of algebraic exercise. So, the crux of it is that we do a small signal harmonic analysis. So, you given a current as the input which is about a certain bias, there is a small modulation Jm. So, you assume that Jm is very small when compared to Jb, there is a small signal part, and you are assuming that the injection current is sinusoidal. So, you are doing a harmonic analysis. So, you assume a frequency omega. So, the consequence of that is you will have the carrier density oscillating at the same oscillation. If there is any delay, that will come up in the solution for the carrier density, and correspondingly as a carrier density oscillates, the photon density also oscillates. So, you assume that the photon density oscillates at this frequency. So, note that your if there is any delay in the system, that will come out as in the complex response. Okay. So, what we did is we first substituted this into the photon density equation, then got some nice relation between the modulated power and the modulating carrier density, and then we substituted this into the photon carrier density equation and did some algebra, and finally came up with the transfer function which looks like this. Okay. And what we are interested to know is that, of course, in case of LEDs, we found this was like a low pass filter. There was only one term, j omega term at the denominator, and that was immediately looking like that of a low pass filter. And we said, okay, the response is given by characterized by the recombination time tau c. But in case of lasers, what it is coming out is that there is a omega square dependence, there is an omega dependence, and there is a constant dependence. That is a first striking feature, which means it is like a resonator now, and obviously laser is a resonator. So, that resonator response has to come out. Okay. So, it is like a oscillator which has some resonant frequency, and then there is some damping terms here. Okay. So, we would like to know what is the resonant frequency of the system, and the quickest way, of course, you can do Laplace analysis on this to find the resonant frequency, what is the damping and so on, but the quickest way of finding out the resonant frequency is just make sure that your denominator is maximum, or you find the extremum by doing a first derivative of the denominator with omega. So, but remember, this has amplitude and frequency and phase response. So, you will do the magnitude response, and you do that d by d mod denominator by d omega, you will end up with a frequency, and d by d omega equal to 0, this is the condition you are applying. With that, you will end up with the resonant frequency, and that resonant frequency turns out to be interesting. It has two components. One is our Gn, and we will remind ourselves what this Gn is. What was our definition of Gn? We redefined some parameter as Gn, which was 2 gamma A Vg. So, let us keep ourselves reminded. Gamma is confinement factor, A is a gain coefficient which has the spectral dependence, Vg is the group velocity of the information or the light inside the cavity. So, those are all constants. Pb is the, so if you were biasing the, so let us say this is the power, output power or photon number versus current. We know that there is a threshold behavior, and we are trying to bias at this point. Let us say Ib is my bias current, corresponding to that there is a power, that is my Pb, divided by tau p. Tau p is, what does tau p physically mean? It is a photon lifetime, but what does it relate to? The time after which the photon number decays to 1 by e of its original value. So, with what measurable is it related to? Okay. So, photon lifetime is decided by the loss in the system. Larger the loss in the system, the lifetime is going to be smaller. Okay. So, it means that and of course there is a second term which is 1 by tau c and Gn by Pb, sorry, Gn Pb, and 1 by tau c is my related to my spontaneous emission. This is a spontaneous effective lifetime. So, the point is there is a certain resonant frequency in the system is resonating, does not mean that the response is going to be like a LCR resonance curve, because there is also this damping terms, this omega terms are the damping terms. Okay. So, if you plot this, it will turn out that when the laser is above threshold, the contribution of this term is going to be very small when compared to the contribution of the first term. Okay. So, turns out that your resonant frequency is, you will approximate it as Gn Pb divided by tau p, and that comes from the fact that your 1 by tau c is tau c is large. So, 1 by tau c is a small number, and corresponding to that, I mean the addition of these two is going to be much smaller than the first term. So, effectively your resonant frequency is decided by these parameters and also your Pb and also your tau p. So, once you made your cavity, tau p is fixed, R1 R2 is fixed, tau p is fixed. You made your cavity, your material is fixed, Gn is fixed, which means your resonant frequency is proportional to Pb. Now, having this resonant frequency is good or bad for the system? For that you should know how the response of h of j omega is looking like. Okay. So, it turns out that if you plot this mod of h of j omega for reasonable numbers of typical semiconductor lasers, I will redraw this. It is going to look like this: mod of h of j omega versus omega is going to be flat and it is going to look like this. So, the damping is such that it is extending it to, depending on that is actually dependent on the nature of the transfer function. The nature of the transfer function is a heavily damped kind of an oscillator, and it turns out that it is going to look like this, which means if I am modulating my current at a frequency omega which is at lower values, the h of omega is flat, meaning I get a linear response. As I keep increasing my frequency, my system response is constant, which means physically it means that if I modulate my current at a certain frequency, I will get the power corresponding to the same frequency. The system is just going to respond as per my input, that is what it means. But if my modulating current is operating at a frequency which is closer to resonant frequency, the output is now a nonlinear function of the input, right. In the Fourier domain, your input is x of j omega, the system response is h of j omega, right. The output is y of j omega is equal to h of j omega times x of j omega. We already calculated what the x of j omega, h of j omega is. Now, if you are operating at a region which is smaller than the resonant frequency, much smaller than the resonant frequency, your output will just mimic the input. It will still operate as a linear system. But the moment h of j omega does something like this, resonates like this, the system is non-linear. Your h of j omega is a non-linear function, which means that you would be exciting the system with omega, but the system could be responding at higher frequencies, 2 omega frequency or difference frequency or 3 omega frequency or so on, because it is a non-linear response. So, let us ask this question again: is it good to have a resonant frequency, or is it really good to have something like a nonlinear response at the resonant frequency? It's not good to have. Or in other words, this omega r is determining what is the operating frequencies, the speed with which you can operate the laser. And the good thing is, even after you made the laser, there is some way of controlling this resonant frequency, because it is dependent on the bias current. Okay. So, for and one more thing which we will not discuss in detail, but I will try to point out your attention is, you know, this j omega frequency, the j omega coefficient actually determines the damping in the system. We will not go into the detailed Laplace analysis, but you see that Pb is also influencing the damping. So, when I change Pb, not only the resonant frequency changes, but the damping also changes, because you have Pb in this and you have Pb in this. Okay. So, I will tell you the result. What really happens in a laser system is that for a lower value of Pb, let us say this is my response, for a larger value of Pb, which means how do I get a larger value of Pb? I just change my bias current, operating bias current. I change your operating bias current, your response, if you are kind of normalizing with respect to this, the response, first of all, the resonant frequency gets pushed to a larger value, and it turns out that it will start getting damped also. So, for a given laser, you can find out the sweet spot, you can find out the optimal bias current for which, you know, you get a large modulation frequency. But what do you lose when you go further on Pb? You will have to increase Ib. When you increase Ib, what happens? What do you lose? What you gain is, from this Ib to this Ib, your Pb got increased, but what do you lose? For the same depth of modulation, you know, in terms of extinction, the average power will start increasing, right. This is my high, let us say this is my low. So, when your current goes high and low, your output power goes high and low, but my overall average power in the system will start increasing. Now, that may be good, that may be bad, depending on what your situation is, but this is what is a consequence of that. Okay. But the good thing is, if I operate here, I will be able to operate with a larger modulation bandwidth, which means I will be able to feed larger frequencies at the input and still be able to get a good response at the output. So, if you were to actually design a direct modulation transponder or a transmitter, you need to characterize this h of j omega for your packaged laser, because you know you can probably have numbers for R1, R2, tau p and so on, but it will be a good idea to actually characterize it. And how does one characterize it? You basically look, you just like how you would do a transistor frequency response characterization. You change the input frequencies, you look at the response in the optical domain. So, you will excite the system with different frequencies. The system will give you optical power as a function of frequency, that you will have to put it on a photodetector, because you want to convert it into an electrical signal, and assume that the photodetector is not limiting any of the bandwidth of the system. The photodetector is having a very large bandwidth, and then you would change this frequency and look at output by input. Of course, by output by input in this case is you would not look at output by input, but it is h of omega is, we define it as power at omega divided by power at 0. So, without modulation to with modulation, with modulation to without modulation ratio, and find the transfer function, and you will have to repeat it at different IB values to find out where your sweet spot is, and then figure out what should be the operating bandwidth. Okay. But overall, if you calculate this number for laser, you see tau c is nowhere in the picture. LED, it was limited by tau c. Here it is going to get limited by tau p, and tau p is something that is loss in the system, and that is something that we are designing. I mean, of course, there is some inherent loss in the system, but the mirror loss is something that we are designing. So, you can control the modulation bandwidth in general. Okay. And the state of the art today is people have done direct modulation lasers. So, these are direct modulation lasers, meaning you are directly modulating the current of the laser to get the power as on and off. 25 gigabits per second is common. You can get transponders which work at 25 gigabits per second. So, the bandwidth corresponding to that would be something like 18 gigahertz or 20 gigahertz kind of bandwidth. There could be one-off demonstration. It's always useful to have this direct modulation on-off. If you just want on-off signaling, you are better off doing this. You just modulate the current of the system, your output gets. So, this is the simplest way of modulating, and there could be state of the art demonstrations in the lab which may have gone even up to 40 gigahertz or so on, because the fundamental limit is here you want to improve on the gain of the system, and also you want to improve, you want to kind of have a trade off for the loss in the system. That is the design parameter. Okay. So, you can, so when compared to LED, you can go all the way up to LED. We said it is of the order of, what was the order of modulation bandwidth for LED? Of the order of megahertz. Okay. Whereas lasers, you can always go up to even much larger than 10 gigahertz also. Okay. So, two problems we had with LED. One was the spectral width, large spectral width. That problem we reduced by putting mirrors, putting resonators, operating in fundamental mode and getting a reduced spectrum in laser. So, that problem is solved. Second problem was modulation bandwidth, limited modulation bandwidth, and now we are saying that we are going, because of stimulated emission, we are able to go out of the regime of spontaneous emission. So, the system is not limited by the spontaneous recombination time, it is decided by the photon lifetime in the cavity. Okay. So, those two problems are solved. So, lasers are much better than LEDs, but before we conclude on transmitters, we should also look at what are the limitations of using lasers. It cannot be like everything is so good, right. So, you should look at what are the problems. I mean, I can do all this, but what should I remember? Okay, modulation depth. So, the question is about modulation depth. So, let me explain this. Let us say I have a laser whose characteristic is like this. I have a bias, I have a current. So, let us say IM is my peak value and IB is my bias current. IM to IB ratio is telling me if, so this is one case where IM to IB ratio is small. Let me draw another case where IM to IB ratio is large. Here I am modulating, the modulation depth is larger, right. Now, this is in the current domain. Now, when it goes into the optical domain, IB corresponds to a certain PB, IM would correspond to a certain PM. So, I have my optical power going between these two values. So, what decides the modulation depth in the optical domain? Of course, there is an IM by IB, but there is one more conversion factor. Current gets converted to power and you are trying to operate in the linear regime, and what do you call the slope as? The slope efficiency. If I have a poorer slope efficiency, let me think of another laser where the slope efficiency is only this, which means that for the same IM, I am going to get only a smaller PM. So, the depth of modulation that I get in the optical for a given depth of modulation in the electrical domain is decided by my slope efficiency. Here is a case where I took two slope efficiencies, but the same operating point, the average power also changed here. Average power changed not just because PM reduced, it changed because my PB also reduced, because I am using a laser with a poorer slope efficiency. Okay. What I spoke just in the previous slide was that for the same slope efficiency, if I now operate it at another bias point, because it is the same slope efficiency, the modulation depth will not change, but my average power is going to change. And last time we also talked about a situation where whether we want to keep your IB close to the threshold or away from the threshold, and we said operating away from the threshold is a good idea, because you do not want to push your laser back into the spontaneous emission domain. If you push it back to the spontaneous emission domain, what is the consequence? There will be a turn on delay. Okay, so there will be one more additional component of delay in it. So in all your derivations you can't ignore your RSP, right. So you will have to worry about that also. Okay.